members of our group. We are students from the UWM CGCA, and these are some of the upcoming events at the UWM Manfred Olson Planetarium. So if you want to check them out, please feel free to do so. If you have any suggestions for any future talks that you want us to present, please shoot us an email at the email address provided here. And speakers for today are myself and Shashwat. So let's start with this image of a clear night sky. You head out at night, you look up to the sky and you see a sky full of twinkle twinkle little stars. And if you ever wondered what they are, then I'm glad that you are here today, because today we'll be talking about the lifespan of stars. Okay, so let's start with some star facts. Stars are these luminous spheres of plasma. Plasma is hot ionized gas held together by their own gravity. And they appear as fixed points in the sky. Although you will see with changing seasons the position of star changes, but that is not due to the stars moving, but due to the position of Earth changing as it moves around in its orbit. So the view of the sky changes with time. Stars are also a source of a lot of the heavy elements in the universe. For example, the iron in our blood, the oxygen that you have in the air, they are all from stars. In fact, we are all made out of star stuff. Stars appear as these blue, red, yellow dots in the sky, although to the human eyes they appear as pale white dots, because the stars are not bright enough for our eyes to perceive these colors. So they appear pale. And it is estimated that the Milky Way contains around 200 billion stars, although we've only seen about 1 billion of them till date. Now let's move on to where stars are formed. This is the picture of a part of a nebula called the Eagle Nebula, and these are known as the pillars of creation because of this column-like appearance of these gas clouds, and these are places where stars are born. This image is taken in the visible spectrum by the Hubble Space Telescope, but from this image it doesn't seem like there are too many stars here. Maybe there is one big one here, a few small dots here and there, but it doesn't seem like there are too many stars here. So before I move on to a new image, let me take a step aside and show you the electromagnetic spectrum. So light, as you all know, is an electromagnetic wave. So much just like any other wave, it has a wavelength and frequency. And this spectrum shows you the whole range of electromagnetic waves, starting from low energy to high energy, and with the increasing wavelength. So with increasing energy, the frequency, which is the rapidity of these oscillations, increase, but the wavelength decreases, which is the distance between the peaks. And this range from 380 nanometers to around 750 nanometers is the visible range. And by visible, I mean what's visible to our human eyes. And beyond that is the infrared, which is higher wavelength and low energy. And in front of that is the ultraviolet, which is high energy but low wavelength. And this left image here shows you a source, or like instruments that work on some of these, use some of these electromagnetic waves across the whole spectrums with radio waves that radios use. And then there is the UV ray from the sun, the bulbs emit visible light, and so on. Okay, now let's move back to that picture that I showed you before. This was the one taken in visible, which we can see. This is another image of that same area, but taken in infrared by Hubble. And now what you see is this whole place is glittered with a lot of stars. And this kind of shows you that this is really a place with high star formation activity. So these places, like nebulas, gas clouds, are where stars are born. Now that we know how stars are born, let's move to how they're born. Okay, so like I told you, they are born in these gas clouds. And what happens is the gas clouds start contracting under their own gravity. And when they collapse, the temperature of the gas clouds increase due to gravitational contraction. Kinetic energy of the gas molecules, which increase the gas pressure, and it starts pushing outwards and preventing the gas cloud from collapsing. But if the gas cloud has a sufficient enough density and mass, it can go on contracting by overpowering that outward pressure. And that happens as is explained in this diagram. And the criteria that is required to meet is called Jeans instability, which was like worked out by James Jeans, pictured here. So what you have here is a gas cloud. It has gas pressure pointing outwards while gravity is trying to pull it in. And now, depending on the size of the gas cloud, a larger gas cloud will require more mass for gravity to overpower this outward pressure. But what usually happens is, instead of this whole large gas cloud collapsing, smaller fragments inside the gas cloud, which have small radius, start collapsing because they meet the Jeans instability criteria. And what ends up happening is formation of these smaller stars within a large gas cloud, which is what you saw in the picture. There was this huge gas cloud, but it was filled with small stars everywhere. Okay. Now that we know that due to, like, when the Jeans criteria is met, it leads to this runaway contraction, which is the gravity pushing the clouds in together endlessly, there has to be a way to prevent that from happening at some point. And what happens is, as the gas cloud keeps contracting and the temperature rises, when it reaches a high enough temperature, hydrogen fusion begins in the core of these gas clouds. So once hydrogen fusion starts, it releases a lot of energy which heats up the gas, as well as the radiation pressure that it generates, that balances the inward gravity that's trying to pull it in together. And this diagram here shows you that in this core there is fusion happening, which is generating heat and pressure outwards, while gravity is trying to pull everything in, and they remain in a state of hydrostatic equilibrium where the outward pressure matches the gravity that's trying to pull it in. And this is how a star is formed. Okay, now that we know about how a star is formed, let's talk a little more about this fusion process that takes place inside stars. So in 1920, Arthur Eddington proposed this idea that stars fuse hydrogen, and that is the source of their energy. But at that time, science was not as developed, and a lot of people doubted this idea, saying that stars weren't hot enough. And to that, Eddington remarked with this line, which is basically a polite way of saying everyone is doubters to be off. So, well, the doubters had their reasons for that. Now, we know that hydrogen is basically a proton, which is a charged particle. And when two charged particles come close to each other, they repel and try to go back, far away. So a bit of calculation shows that if two hydrogen atoms have to overcome this Coulomb repulsion, they need to be at a temperature of 10 billion kelvins so that the hydrogen atoms can fuse, which is a lot. Whereas the gravitational contraction, which heats up the gas cloud, for a gas cloud with the size of our mass of our sun, the temperature that it can reach is about 10 million kelvins, which compared to the 10 billion is not much. So the doubters had reasons for not agreeing with him. Now, just to give you an idea of how large these temperatures are, water freezes at 32 degrees Fahrenheit, which is 273 kelvins, and it boils at 212 Fahrenheit, which is just 373 kelvins. So now you kind of know why Eddington was not happy with the people who were saying, like, complaining about stars not being hot enough. Okay, so this is a problem. So what's the solution? The solution was given by George Gamow, who presented his theory on nuclear fusion. So this diagram here shows you the potential energy of two approaching nuclei, in this case the hydrogen. And this peak that you see here is the Coulomb barrier, or the Coulomb potential that the two approaching nuclei need to overcome. So if a hydrogen atom approaches another one, it has to rise up along this potential here in order to reach to a close enough distance where strong nuclear forces take over and the force becomes attractive. But like I said, a bit of calculation, classical calculation, shows that this requires a temperature of 10 billion kelvins, which is not possible. So the probability of this happening is 0 according to classical physics. But what George Gamow showed is that instead of jumping this barrier, what a hydrogen atom can do is instead tunnel through this barrier. And there is now, because of this, like this is a quantum mechanical phenomena called tunneling. Because of this, what was originally a zero chance of occurring now has a small but non-zero probability of happening, which is two hydrogen atoms fusing. Now, inside the core of a star, there's a lot of hydrogen, like huge numbers, and the density is high. So even a small non-zero probability of fusion is enough to generate significant number of fusion reactions in the core of the star. Okay. So now that we know that fusion is indeed possible inside the core of a star at much lower temperatures, let's move on to see what different kind of fusion reactions are possible. So the main stellar nucleosynthesis processes, the first one is hydrogen burning, which happens in every star. There are two pathways for this. First is the proton-proton chain, and then the other one is the CNO cycle. This was worked out for the first time by Hans Bethe, who won the Nobel Prize in Physics in 1967 for this whole calculation. Now, after that, there are burning of heavier elements like helium and then oxygen, neon, carbon, and lithium, which can happen in stars, and this was worked out by Fred Hoyle. Okay, now that we know about some of the different processes by which stars can produce energy to prevent itself from collapsing, let's look a bit closely at the different stages. So the first one, like I said, hydrogen burning through the proton-proton chain. So this one occurs in stars with masses of about the same as our sun or lower. And this diagram here shows you that you start with 4 hydrogen atoms, which are basically protons, and you end up with a helium-4 nucleus, which is 2 protons and 2 neutrons together. And this is dominant at about 4 million Kelvin temperatures, which is more than like stars. In fact, our sun's core temperature is more than this. So this process occurs inside our sun. The end product, as I said, is helium. Now, in our sun, it's burning hydrogen, or basically protons, at a rate of 4 times 10 raised to the power 38, which is like 4 followed by 38 zeros, number of protons per second, which seems like, in fact, it is a very, very high rate. But even with this high rate, our sun can keep burning hydrogen for another 5 billion years, which is a lot. In fact, when the sun started out, it had enough hydrogen to burn for 10 billion years, and it's already done so for about 4.6 billion. So it's still got another halfway to go. Okay, the next pathway for hydrogen burning is this carbon, nitrogen, oxygen, or CNO cycle. From the diagram, you can see why it's a cycle. It's the cyclic process involving carbon, nitrogen, and oxygen, and the end product is the formation of helium once again. But this occurs in stars which are much heavier than our sun. In fact, when our sun gets heavier, this process will start to dominate, and it dominates at a temperature of about 18 million kelvins. The core of our sun is at around 15 million kelvins right now, so pretty soon, or well, not soon, but soon in astronomical timescales, it will start like producing more helium through CNO cycle. But right now, only 2% of the helium that's produced in the core of the star, of our sun, is through the CNO cycle. And this was kind of a theoretical prediction for a long time, until in 2020, when first experimental confirmation was done for the presence or the occurrence of CNO cycle inside the core of our star, of the sun. And it was done in 2020 by studying the neutrinos that you see here that are emitted. Okay, now that we are done with hydrogen burning, which occurs in every star, next we move on to helium burning, which is a heavier element. And by heavier element, what I mean is, for say, suppose in helium, you see there are 4 constituent particles in the nucleus. A heavier element is something where the number of constituent particles in the nucleus is more. Like, for example, in carbon, you see there are 12 dots here. So the next stage of stellar evolution involves helium burning, and it involves this hydrogen triple alpha process. Now, alpha particle refers to basically a helium-4 nucleus with 2 protons and 2 neutrons. And as the sun or any star keeps burning hydrogen and producing helium, all the helium gets dumped in the core, while the lighter hydrogen is pushed outwards as a shell around that helium core. Now, what ends up happening is, over time, as the amount of helium increases and hydrogen from the core is pushed out, the outer shell doesn't have enough temperature to sustain hydrogen burning. So the star starts contracting, and the core temperature keeps increasing to, and as it reaches a temperature of around 100 million Kelvin, the core is hot enough to start burning helium, or helium fusion. So this process is where 3 helium nucleus combine to form a carbon, and this carbon can in fact combine with another helium nucleus to generate oxygen, and this oxygen and carbon can take part in the CNO cycle that I was talking about before. So the core of this star burns helium, while outside in a shell there is hydrogen burning. Okay. In fact, this step also happens in most of the star. In our sun will also reach a stage where it will start burning helium. Okay. Now, what about the heavier elements that I was talking about before? Iron, oxygen, where do they come from? Well, not all stars can generate enough heat to start fusion of these heavier elements beyond helium. But if a star starts with a mass of 8 times the mass of our sun, this M dot symbol represents a solar mass. If a star at birth has a mass more than 8 times the mass of our sun, it will reach sufficient temperatures to burn elements beyond helium. So what are the different processes possible? I have listed here all of them in the order of the occurrence, starting with carbon burning, which occurs at a 500 million Kelvin temperature, and all these occur in the core of the star, followed by neon burning, which occurs at 1 billion, then oxygen burning at 2 billion, and then silicon burning with 3 billion. Now, silicon burning leads to the formation of iron, which is the last step in this nuclear fusion process inside a star. No further fusion reaction is possible in a star beyond the formation of iron. Okay, now that we know how stars sustain themselves from collapsing under their own gravity due to their own mass, how will we classify the different stars that we see in the sky? Let's talk about them. Okay, so this image that you see right here was taken by Hubble. This is in the visible range, so our human eyes can see it, but this is taken by Hubble in a clear out in the space. This is the core of a globular cluster called Omega Centauri. And what you see here is this whole place is filled with different color of stars, like red, blue, some yellows and oranges and white dots, and each have varying intensities or brightnesses. So this picture kind of gives us an idea of what different ways we could start classifying the stars. It could be the color or how bright they are. So let's talk about some of them. The first one is the color of a star. So stars are considered to be black bodies, and what I mean by that is that they emit light across the whole range of frequencies or wavelengths that I initially showed you. So this plot right here is the plot of radiation emitted by a black body, and it's related to the temperature of the black body, so surface temperature in fact. So let's look at this top curve. It's at 5000 Kelvin, which is the temperature of that object, and it has a peak here in the visible range of light, and with decreasing temperature you can see that the peak kind of shifts towards higher wavelengths while the height of the peak decreases. What that means is, with decreasing temperature, the amount of energy that's emitted decreases, so the area under the curve decreases, hence the peak also decreases in height, and the frequency of the photons or the light that's being emitted also decreases because energy is proportional to the frequency. So lower the energy, lower the frequency, and higher the wavelength, so the peak also shifts. But now for some object which has a 5000 Kelvin temperature, you see that it peaks somewhere in this green colored area in the visible region. But that does not mean that the object will appear green to our eyes. What we instead see is not a single color, but a composition of all the colors in this visible range. So instead of seeing something green, what we can see is a sum of all these colors starting at this purple to all the way to red, and an object which is at a temperature of 5000 Kelvin will instead appear white. And so that's one of the reasons why there are no green stars, but you can see blue or red stars because the star could be hot enough that this peak shifts all the way to ultraviolet or beyond, and in that case, as you can see, about the peak, the curve falls sharply, so it will have enough intensity in this blue range of visible spectrum, but not enough in the red, so it appears blue. And again, if the temperature is very low, it might peak somewhere in this infrared range, and there will be some amount of radiation from this red part of the visible range, but not enough in blue, so a low temperature star will appear red. That's why there are red and blue stars, but no green stars, although we see white stars, which is when they have a temperature of around 5000, and then some pale yellow stars as well. Our sun is at a temperature of 5772 kelvins, the surface temperature, and as you can already see, it appears white or kind of a pale yellow color because it peaks somewhere in this green, sky blue kind of range. Okay, now that I've talked about the colors of star, let's move on to one of the earliest serious attempts at classifying stars, and this was done by Annie Jump Cannon, who made a classification system based on the temperature and colors of star, and it was named the Harvard classification system because she was working at the Harvard Observatory at that time. So what she arranged was stars according to temperatures, where she assigned an alphabet of O to the hottest stars, which appear blue and have a temperature of around 28,000 kelvins, which is very hot. This is the surface temperature, in fact. So it appears blue, and the subsequent alphabets are for stars with a lower surface temperature, and the M-type stars are the coolest, and they appear red and have a surface temperature of around 3500 kelvins. Our sun is a G-type star, and this diagram here gives you an idea of how the radius of the star changes with the different types. Now, you might be wondering, why is the alphabets not in the alphabetical order? Why does it start with O? So the story is that when Annie Cannon was working on this classification, there was another classification system in place where people assigned the alphabets according to the amount of hydrogen they had inside a star. So a star with a lot of hydrogen was assigned A, and a little bit less B, and the other letters followed. So when she realized that stars could be arranged according to their temperature, she found that stars which in the original system were assigned the alphabet O were the hottest, while the ones which were assigned M in the original system are the coolest. And these are according to the temperature, but conforming to the original system. And she also devised a mnemonic to help the students at that time remember this sequence of alphabets, which is, oh, be a fine girl, kiss me. In fact, you can replace girl with guy and it still works. Okay, now that I've done that one, the next thing that I'm going to talk about is, well, they are stars too, but not the kind I'm talking about today. So let's move on. What I wanted to say is metallicity and not Metallica. Okay, so what do we know about metals? This is a periodic table which you will see in chemistry classes a lot. In fact, in schools, you'll see this quite a lot. So this is a list of all the elements that are present in the universe arranged according to their number of protons that are present inside the nucleus. And this has a lot of elements which are considered to be metals, and then a lot which are considered to be non-metals. So what are metals? We know them as these shiny, hard objects which are malleable, and they are good conductors of heat and electricity. And I've put some pictures of some of them, like aluminium, copper, magnesium, titanium, and the position of these elements in the periodic table. They are mostly found as solids at room temperature, with the exception of mercury, which is, as you all know, in the thermometer, mercury is liquid. And what are nonmetals? They are these non-lustrous, brittle objects which can be found as solids, liquids, or gas, like the oxygen, like carbon and sulfur are considered to be nonmetals, and I've shown their position in the periodic table here. However, for an astronomer, anything that is not hydrogen or helium, or rather anything that's heavier than hydrogen or helium, is considered to be a metal. So, in fact, it's almost the entire periodic table except for the first two, which is hydrogen and helium. Everything here is a metal. And when we measure the metallicity of a star, what we mean is the measurement of the abundance of these heavier elements that are present inside a star. Because like I told you, stars fuse hydrogen, helium to form heavier elements. So a measurement of these can kind of give you an idea of how, like which stage of evolution that star is in. Now, when we measure metallicity of a star, we don't really measure the amount of heavier elements that's present inside a star, but rather the heavy elements that's present in the surrounding environment of a star, because stars release stellar winds through which elements from inside the star are released outside. So when we study the light emitted by the star, it passes through this atmosphere, and by studying it, we can kind of figure out at what stage the star is in. Now also, like I told you, metallicity is also an indicator when a star was formed. And based on this, so why is that? So right now, the amount of stars we have in our universe, as we go back in time, the number of stars decreased. So what would happen is the presence of these heavier elements would also decrease as we go back in time, because the stars are the source of these heavier elements. So stars that are formed much earlier in the universe will have low amounts of these heavier elements inside, whereas stars which are formed much very recently will have more of these heavy elements. So based on this, there are two different ways of classifying stars. One is the population 1 star, which are metal rich and young stars because they are formed very recently. And then there is the population 2 stars, which are metal poor and old stars, and they were formed very early in the universe. Now, this is not where the story ends with classifying according to metallicity. There is another population of stars, but I'll come back to that later. Okay, now let's move on and talk about magnitude. And magnitude is a measure of the brightness of an object. And there are two different ways of measuring magnitude. One is the apparent magnitude, which is the brightness with which an object appears from Earth. It depends on the distance of that object from Earth. And the other one is the absolute magnitude, which is a measure of the intrinsic brightness of a star. Now, this diagram here shows you a comparison between the two scales, the absolute magnitude plotted on the top and the apparent magnitude in the bottom, with the apparent and absolute magnitudes of a lot of objects in space, mostly stars. And I've written here that lower is higher, by which I mean that lower the number, higher is the brightness. Why is that? It sounds kind of counterintuitive. Well, there's a historical reason for that. The earliest known magnitude system was developed by a Greek astronomer called Hipparchus, who catalogued a lot of stars that he saw in the night sky and assigned a magnitude of 1 to the brightest stars, while a magnitude of 6 to the faintest ones. So as the magnitude system kept evolving over time, it was made in accordance with the previous system, and this way of reverse way of assigning magnitudes stuck. But it works, so we are still using it. Now let's make a little more sense out of what this diagram is telling us. Let's look at the sun. Our sun has an apparent magnitude of -27, while an absolute magnitude of around 5. Now the apparent magnitude tells us that the sun is very bright, while the absolute magnitude tells that it's not really bright at all. For reference, let's look at another star, Regulus, in this green box. It has an absolute magnitude of -5, which means that it's brighter than the sun. Whereas if you go to the apparent magnitude, it tells you that its apparent magnitude is around -1, which is fainter than the sun. So what's happening here? Well, what this means is that because the sun is so close to us compared to a star like Regulus, which is very far, it appears very bright in the sky. But if you place them at the same distance from the sun, suppose Regulus were to be placed at the same position our sun is, Regulus would outshine the sun in brightness. But just because it's very far away compared to the sun, it apparently is less brighter than the sun. Okay. Next, let's talk about the Hertzsprung-Russell diagram, which is a culmination of the different classification schemes that I talked to you about. It was developed by Einar Hertzsprung and Henry Norris Russell in the early 1900s. And this is the diagram, which is a culmination of all the different things. So what does it show? It is a plot of the surface temperature of a star against its luminosity, which is the theoretical HR diagram. But there are other variations of it, one of which is the plot of the color of a star against its absolute magnitude, which is often referred to as the color magnitude diagram. And as you can see here, the different regions in this HR diagram are the different stages of evolution of a star. So there are three main regions here. One is the main sequence, which is this big red line, which is kind of splitting the plot in half. There are the red giants and the supergiants, which is way up here. And then there are the white dwarfs. The names kind of give you an idea of how big these, like the sizes of these objects. Okay, so this is like basically all the stars that you see in our universe can be classified on this HR diagram. Okay. And yes, so sun is a main sequence star right now. It will later move on to a giant phase, but we'll come back to that later. Okay, now that I've talked to you about how a star is born, where it's formed, how it keeps itself from like collapsing under its own gravity, and how we classify them, let's talk about the ones who could have been stars. They are the brown dwarfs, or as often they are called, the failed stars. Now, like I told you, when a cloud of gas contracts under gravity, it heats up. But if the mass of that cloud of gas is not high enough, it won't reach enough temperatures to start hydrogen fusion in its core. And that's when a brown dwarf is formed. So these are somewhere between a gas giant planet like Jupiter in our solar system and our sun. And they have masses ranging from 13 to 80 times the mass of Jupiter. And the energy that they emit is mainly from the heat that's trapped inside these gas clouds when they contract. And the warmest of these brown dwarfs appear orange, which kind of gives you an idea of their temperature, because they are not hot enough. They don't release very high frequency radiation, so they appear orange. While the coolest brown dwarfs that have been detected are in fact out of the visible range of colors, visible electromagnetic range. And they are mostly seen in the infrared, so our eyes don't see it, but infrared telescopes can. In fact, one of the coolest brown dwarf that has been discovered has a temperature of just 300 kelvins, the surface temperature, which is the same as the temperature of a human body. Okay. Next, I'm going to talk about are the stars which were born or formed at the dawn of the universe. Now, when I talked to you about metallicity, I told you about these two population of stars. One was the population 1 star, which have high metallicity, they are metal rich and very young. And then the population 2 stars, which have low metallicity, they are metal poor and they are old. However, when the universe was formed, the earliest elements that were formed after Big Bang was only hydrogen and helium with very trace amounts of lithium and beryllium. And even the population 2 stars have high enough metallicity that it's not possible for them to have formed at such an early stage of the universe. So next what we did was a new category is developed called population 3 stars, which are formed entirely out of hydrogen and helium, and they formed very early in the universe, and they are formed of these primordial gases, hydrogen and helium. And these stars were in fact responsible for producing like the earliest heavy elements in the universe. Now, we haven't made any confirmed detection of these stars yet, and one of the possible reasons for that is these stars could have been very massive with masses of about 300 times the mass of our sun, which is huge. And because of that, because they had such a high mass, they had immense gravitational fields and their cores were at a very high temperature. And as a result of that, the hydrogen fusion reactions that were occurring inside their cores was very fast. The rates were very fast. So they lived fast, died young, and what's left behind is their remnants, like the black holes or the white dwarfs. Now, just by looking at the remnants, we cannot guess what kind of stars they were before, so it's hard for us to figure out whether really there was population 3 star or not. However, recently, James Webb Space Telescope, which was launched very recently, detected a star which is like the farthest star detected till date at 28 billion light years away, which means that the light that we are seeing now, or James Webb detected now, was emitted by the star 28 billion years ago, which is like a long, long time back. And this dot right here in this arc is basically the host galaxy of that star, which has been named Yarendel. For those of you who are into Lord of the Rings, you might know this name. So this point right here is that star, which is the farthest star detected till date. And people think that this might, like, potentially could be a population 3 star. Okay, now that I've talked to you about how a star is formed, I introduced 2 different ways the star can be classified, as well as the different types of stars.
Most of these are spectral class B, and these are stars above 8 solar masses. So this is a star that is destined to die with a bang. There is no doubt about it. So it will start off very hot and blue, and then slowly as it cools down, it'll turn red, and then it's going to die with a bang. All right. So since we've been talking about big stars, hypergiants, let's talk about some of the biggest stars that we've seen so far. One example is UY Scuti. So it is a star 9,500 light years away from us, and it has a radius that is 1,700 times that of the sun. So it's a very, very large star. But largest star does not mean the most massive, because our sun will also expand massively, but it'll still have the same mass. So the most massive star that we found is actually this one called R136A1. It is 196 times the mass of the sun. And this is really pushing the envelope for what we think a star can be. We think that the upper bounds are about 200 solar masses, although population 3 stars may have been even more. So this is really a monster, and we're having trouble trying to comprehend this thing. All right, so now we've talked about retirement, how stars slowly run out of hydrogen and then begin to convert helium. And this is what happens once they're done with that process as well. So here's what's going to happen to our sun, but we have time. So we've talked about the main sequence. We've talked about it running out of hydrogen in the core and becoming a giant. And now we're here to talk about how it's going to die. There's a couple of ways this could happen. So here's just a diagram of the onion-like layers of a star as it begins producing different elements, and you go down towards the core. So how does a star die? Well, there's 2 main ways, and then a third interesting concept we'll look at. So a star could just run out of fuel. It just does not have enough mass to keep going beyond helium or carbon, and it just kind of gives up. Another reason is it could create iron, and this is when a star dies with a bang. And if a star is unlucky enough to be born with siblings, the siblings might do some crazy things to the star and disrupt it as well. So we're going to go through each of these possibilities, and they're all very unique and interesting. So let's talk about dying with a whimper. This is what's going to happen to our sun. So as Tamal mentioned, less than 8 solar masses is not massive enough to die with an explosion. So once a star goes into its red giant phase, slowly as the core contracts and the outer layers get spread out, eventually the outer layers are completely shed away, and all that's left is this dense inert core where fusion no longer happens. So for our sun, we expect that core is going to be carbon and oxygen, because no more fusion will occur once those products are made. And the reason why this object is left is because so much pressure has compacted this object to the point where the electrons are forced into their lowest energies. So it's really the electromagnetic forces keeping the star from collapsing fully. The electrons have nowhere else to go. They push against each other. And so this is a very dense object. It's about the mass of the sun packed into an area the size of Earth. So this is a very dense object, and it's very hot as well. And it'll continue to be hot for millions and billions of years. So dying with a bang, I mentioned iron. And these are what happens to stars when they're above 8 solar masses. And once the core gets to about 1 to 3 times the mass of the sun, things aren't going well. So if the star can make elements beyond oxygen, it eventually reaches iron, and then there's nothing that can hold back the star. Iron is a star killer, and we'll go over why that is. But like I talked about the white dwarf, what can happen is if there's so much gravity that even the electrons are forced into their nuclei, protons start becoming neutrons. And now all that's stopping collapse is these neutrons packed as tightly together as possible. So this material is sometimes called neutronium, and it's about 100 million tons within a small cubic centimeter. So this is extremely dense. It's what neutron stars are made of. So if there's enough gravity, it doesn't become a white dwarf anymore, it becomes a neutron star. And so this is an object with the mass of the sun packed into the size of a city. So much, much denser than white dwarfs, much, much more powerful objects. Now, if even the neutrons can't hold back gravitational collapse, well, you've got a black hole then. Nothing can escape this, not even light. So this is the way a star that's big enough can die and end up as these very powerful gravitationally pulling objects. So I mentioned iron is the star killer. Why is that though? I mean, you use iron all the time. It's not really that dangerous. But the reasoning is because iron is stable. So if you look at this graph, this actually shows negative numbers. So it's kind of a confusing graph to analyze, but what you need to know is that lighter elements aren't as stable. So hydrogen is not very stable, and it prefers to join up with other elements to form heavier elements. So this side of the graph is unstable, and they prefer to come together to stabilize. Whereas this side of the graph, you might notice uranium, and uranium is famous for being radioactive. That's because uranium is too big and too unstable, so it prefers to actually decay to lighter elements. And once you hit iron, it's the most stable. So once you fuse to form iron, there's not enough energy being produced back to push back against the star's gravitational collapse. And now this balance of hydrostatic equilibrium, where radiation is pushing out, gravity is pushing in, is no longer preserved. And once the star makes iron, its fate is sealed. It's going to collapse in on itself. So let's talk about the third type of way a star can die. If it has a sibling, weird things can happen. So if a star has a sibling that's further into its evolution and becomes a white dwarf, and the star is able to survive this red giant phase, the white dwarf is so dense that it can start to strip material away from its sibling. And this material falls in rapidly onto the white dwarf, and as it falls in, it heats up, and it can trigger nuclear fusion once again. So this is almost like a zombie star, a star that stopped fusion and has now brought it back. But this doesn't last very long, because once the white dwarf accumulates enough mass, it collapses and triggers a type 1a supernova. So these things are very useful in astronomy. They're used as distance markers. And if the star can survive the supernova, well, it's going to be given enough energy that it's just pushed away completely from where it is. So a star can get a kick from its sibling when it goes supernova, and the star is just flung away. And these supernovae can outshine entire host galaxies. So these are very, very powerful events. If it's unluckier and doesn't have a white dwarf, but instead has a neutron star, the neutron star can do the same thing and strip material away from its sibling and actually speed up. So some of these neutron stars can be sped up so that they spin hundreds of thousands of times per second. So they're being devoured for speed, or it can just be devoured by a black hole. So it's better to just be alone in this case if you're a star. So the summary, we'll go over that picture I've been showing you. As you can see, if you don't have enough mass, you're just a brown dwarf and you can't trigger fusion. If you have enough mass around the mass of the sun, you'll eventually go through the main sequence, turn into a red giant, turn into a white dwarf, and then eventually the white dwarf could explode if it accretes matter. If you're a little more massive, you become a supergiant, and then you go into this path where you either become a black hole or a white dwarf. So that, a black hole or a neutron star. So low mass stars, white dwarfs, massive stars, black holes or neutron stars. And this is the path that they take. So here's just an explanation. Tamal has shown you a few periodic tables, but this one shows you where these elements are made. So as I've said, iron is the last product of fusion in a star, but once the star collapses, it can actually form more elements because the collapse is such an energetic process that you can get elements heavier than iron. And then there's some more interesting things that happen if you get two neutron stars to collide, if you get white dwarfs to explode. So these are how all the elements are made through all these different stellar death processes. And it's really interesting to see there are a few elements that aren't made anywhere but here on Earth. So that's also really interesting to see. And I thought I'd end this talk off by Tamal talk to you about the stars that began at the universe. So these are the stars that will end the universe. So no one's seen any of these as of now, I should just mention, but this is what is expected once a white dwarf cools down after trillions and trillions of years. So somewhere around 10 to the 15 to 10 to the 25 years, these objects will slowly radiate away all their heat and will no longer be visible in infrared either. So there are some candidates of white dwarfs that we think will go down this road, but we don't expect to see any of them anytime soon. And it's just going to take a really, really long time. So no need to feel bummed about it. Stars are still being formed, and we live in a small sliver of time in the universe where all these interesting properties can happen. Because once we reach the age of the black dwarfs, the universe will be populated by black holes, and there will be no more star formation. So this is a wonderful time to live in, is what I'm trying to say. So yeah, I would like to say thank you all for listening, and we have another talk coming up on May 6th. So thank you. Questions?
What class of stars, like what size of stars are big enough to create like stellar nebula to create more next generation stars?
So yeah, that's a really good question. Most stars, when they explode, if they don't form black holes that devour everything that's left, so once a white dwarf is formed, also the outer layers shed and form a nebula, and other stars that explode so violently that they leave nothing behind form these nebulae. So around 8 solar masses would form like a planetary nebula. Good question. I think it's about, the question is how far deep into the sun do you have to go to get to the core? It's an interesting question. I think it's about 2/3 of the way in. Yeah, that would be my guess. I don't have an exact answer, unfortunately.
So the sun is mostly core. 2/3 core, 1/3.
Oh, no, 2/3 down, yeah. Yeah, so there's quite a few layers. There's the invisible coronal layer and stuff, so it goes down pretty deep.
Is the classification of everything heavier than helium as a metal just for convenience, or?
Pretty much, yeah. I think so. It's something I've been wondering myself. Yeah, so the question is, why do some sibling stars actually evolve at different rates if they're usually formed in the same region? One of the reasons could be that, like as Tamal explained with Jean's instability, one of the stars could just be formed from a much larger gas cloud. It's also possible that one of the stars isn't formed from at the same time, and it's kind of wandered in if it's been given a kick from before. So there's a lot of different ways, but you could just have stars that form with different masses at the beginning. Oh.
Alright, so it might be a dumb question, but so a supernova is an explosion that pushes everything out, and a black hole is the universe that sucks everything in. That's the way of thinking of it, or does that not make sense?
So the question is, do white dwarfs, you're kind of asking, are white dwarfs the inverse of black holes, kind of?
Pretty much, yeah.
Okay, I wouldn't say that's the right way of thinking of it. A white dwarf is just, a supernova is the opposite of a black hole, is what you said, right? Yeah, so a supernova is just an explosion, and a black hole is more like a region of space where things fall in, and it's not so much sucking things in, it acts just like any other massive body, so things will orbit it, they don't just fall in. But a supernova is more of just an event, like when the star explodes, so they're not really like classifiable on the same thing. Yeah.
Kind of along that same line with supernova, what do we see from Earth when something goes supernova?
You want to answer this one?
Actually, there was a supernova.
Oh. So the question was, what do we see from Earth when we see a supernova, right?
So there was a supernova explosion that was seen from Earth a long time back. Like there are historical records of it, which is now called the Crab Nebula. It was bright enough to be seen in the daylight as well. But after that, we haven't really seen anything that's like at least visible from Earth by the human eyes. But we have seen supernovas through radio telescopes or other telescopes that are in space. So they are visible, but they aren't bright enough, or they haven't happened with enough brightness in the visible range of light for them to be visible from Earth, at least not in the present day.
Will we know ahead of time when something is coming up?
Well, yeah, kind of. We can, like when we study a star, we can kind of figure out at what stage, like I told you about studying the metallicity, we can kind of figure out at what stage of its evolution it's in. So we can kind of figure out or predict when that star might explode. Although humans don't, like the lifetime of humans is quite low. So the astronomical time scale is so large that we might not even see something happen anytime soon.
Oh, yeah. Okay, so you were talking about hydrogen fusion, talking about nuclei coming closer together.
Yeah.
The way you described it, you kind of created strong force multiplication.
Yeah, actually, there is strong forces. In fact, work at very short distances between the constituent, like the neutrons or protons.
So it's a
Basically,
a component of
yeah, there are
the
four
protons.
types of forces:
Yeah.
electromagnetic, strong force, weak force, and then there's the other type of force. Yeah, gravity. Sorry, I forget. So strong forces are present only inside the nucleus of an atom. Yeah, and they dominate over the Coulomb repulsion only at very small distances, and that's why there is this, like, instead of the peak of Coulomb force rising all the way up, after some point it falls down. And that's what the approaching nucleus needs to overcome.
There's no other questions. Thank you all so much for coming.